Hi everyone, I'm Mohammad Aman Sheikh. I'm here to present my study, Streamlining DevOps, Automating Testing Deployment of Kubernetes Environment. As a part of the study, I'll be discussing, as part of this presentation, I will be introducing you to the DevOps world and importance and showcasing the importance of Kubernetes and use of Kubernetes in containerization and why is the Kubernetes used by most of the organization. And next, I'll be discussing the research idea or the research questions. Then I'll be showcasing the tools used and importance of each tools. And then I'll be demonstrating the architecture design of my study and then the implementation and methodology. Finally, concluding the presentation with the evaluation matrix and providing the future researchers or the future contributors a research idea. DevOps has transformed the software development process by making it quicker and more reliable. Kubernetes is the most famous and leading tool when the architecture used for deployment is microservice. Kubernetes simplifies the deployment process, management of containerized application, auto-scaling, benefiting organization with high availability and optimized resource consumption. But when but with this all benefits, there comes the challenges such as management of configuration, handling security related issue carefully, etc. Hence this research address this complexity by providing a workflow and combining different tools to achieve a streamlined, robust solution. Now let's discuss the research question and research idea of this study. To implement the study, the complete research was divided in following sub-question. How can one automate the complete process, that is to identify the suitable CI/CD tool based on our requirements? How can the optimization of Helm charts be done? Helm being an important deployment tool used in our study, so it was needed to optimize the Helm chart to achieve an efficient Helm chart and deploy using that. Then comes the how can the static code of application be evaluated and improved? Exploration of method to store Helm chart securely and studying its efficiency. There was need to enable versioning in Helm chart and to store Helm chart securely. So as a part of this research, we'll be addressing that too. Researching other security practices and configuration that could be implemented. Now let's have a look at the tools used to implement this study. The tools used were kubescore, Sonar Cloud, Helm, Jenkins, and other AWS services were EC2, S3 Bucket, EKS, ECR, and CloudWatch, etc. Kubescore was used to validate the Helm chart and to check for vulnerabilities and security related issue is in the Helm chart. Sonar Cloud was used to check for static vulnerabilities and bug fixes in the static code that was implemented in Django. Helm, it was used as a deployment tool on the EKS cluster. Jenkins was used as a CI/CD pipeline, and it was used to automate the complete task. Other EC2 service was used to configure the Jenkins. S3 bucket was used to store the kubescore result, and EKS it was used to build a cluster, a Kubernetes cluster, and to create a worker nodes. ECR it was used to store the Docker images, and finally the CloudWatch for monitoring purposes. So this is the architecture diagram that was used to implement this study. Firstly, Jenkins was set up on the Amazon EC2 instance, and the Jenkins server had the kubectl, AWS CLI, Helm, Docker, Sonar Scanner, and kubescore installed on it. When the pipeline was first triggered, the code present in the GitHub was first cloned on the Jenkins server, and then using AWS CLI, authentication was made to Amazon EKS. We generated a config file and stored at the part of kube/config. Furthermore, Helm it was authenticated and it was used for creation of Helm chart and finally storage of that Helm charts to Amazon S3 securely. Additionally, Helm used to utilize the configurations and authenticate with the EKS cluster to deploy that application to Amazon EKS. So Helm used to utilize these uh, configurations available from the AWS CLI and deploy that application to Amazon EKS. Furthermore, Docker it was installed on the Jenkins server itself, along with the cloned. There comes the Docker file, and the Docker file was first built, and Docker image. Furthermore, Docker image was created and pushed to the Amazon ECR. And kubescore was used for the configuration analysis of Helm chart. It generated a report and securely stored that into Amazon S3. And finally, in the Sonar Scanner stage of the Sonar Scanner used to first authenticate it using Sonar token, and the static analysis of the code was made. And finally, the analysis was made on the Sonar Cloud dashboard or the Sonar Cloud UI. Now let's discuss the methodology that was used to implement the study. It began with analyzing gaps in the related study or the related works. Then comes the integration of tools like Jenkins, Sonar Cloud, Helm, and kubescore with each other. Then comes the designing of the pipeline. The pipeline stages include performing the AWS actions, static analysis of the code, ECR authentication, Docker image building, and publishing that to ECR repository. Helm configuration check. Here, kubescore was utilized to check the Helm configuration. And finally, deployment of application using Helm. After all the stages, iterative approaches was iteratively improvements were made to the Helm configuration and static code to deliver bug-free and vulnerable robust solution. Now let's see the implementation technique that were employed to implement this study. The Junkie CI/CD pipeline was set up on Amazon EC2. The pipeline had different stages for static analysis of code, analysis of Helm chart, building Docker image, and finally pushing the ECR, and finally deploying the application to EKS. Helm charts were stored in Amazon S3 using OCI compliance mechanism, enabling versioning in Helm chart and storing securely. Now let's have a demonstration of the study and complete an understanding of the pipeline build and the implementation involved. To start with, the complete code was stored on the GitHub. This is the application code or the application folder, and this is the dot properties folder. It contains the configuration or the authentication related to Sonar Cloud. It has the project key, organization key defined, and the login token. The pipeline that was utilized is this, and the definition of the pipeline was pipeline script. The pipeline had different stages built. So, as the first stage of the pipeline, first the Kubernetes configuration was updated to point to the cluster that was utilized in this study, and and then the complete code was cloned on the Jenkins server using the command git clone. Further, at the next stage of the pipeline, static analysis of code was made. It was triggered using the command Sonar Scanner. This Sonar Scanner, when triggered, it used to utilize the dot properties for folder and make the analysis on the Sonar Cloud UI. So these were the some of the security hotspots and issues identified by the Sonar Cloud. And in background, Sonar Cloud was utilizing the quality gate defined manually, and these were the conditions or the uh, conditions that were used to make analysis. And at the next stage of the pipeline, ECR authentication was made using command AWS ECR get login password piped with Docker login. So this used to authenticate the ECR repository, and uh, the repository that was the ECR repository that was utilized was this one. It contained the all the versions of the image that were built and pushed and had the and based on the image tag that was utilized in the Jenkins pipeline. So as a next stage, at the next stage of the Jenkins pipeline, Docker image was built and tagged and then pushed to the repository, to the ECR repository. Further, the Docker file was stored in the along with the basically along with the application. So this is the Docker file that was utilized for this project or for this study, and to create an image and to create an image of Django application. Further, and further in the next stage of the pipeline, Helm configuration check was made. First, the manifest file was created and a common manifest file was generated using Helm get manifest file. Further, kubescore was used to score or make an analysis on that manifest file and generate a updated kubescore result.txt on Jenkins server. And finally, AWS S3CP command was utilized to copy that generated text file into S3 bucket. The text file that was generated or the report that was generated was stored in the S3 bucket in this fashion. And in the final stage of the deployment, final stage of the pipeline, deployment was carried out using Helm. So using Helm repo add command, the Helm chart that was stored in S3 bucket, it was first tagged with the name my-S3 repo, and the Helm repo update command was used to update and point to that my-S3 repo. And finally, Helm upgrade was used to release a new release of the Helm chart by specifying a version flag and pointing to the new version of the Helm chart. Now let's discuss more about the deployment configuration, Helm chart created, and versioning that was employed using OCI mechanism, some for the storage of Helm charts in Amazon S3. So, so this is the Helm chart that was created and Nginx app using Helm create command, Helm create chart command. Now let's see how the versioning was enabled in this Helm chart, and index.yaml was utilized to maintain the versioning of the Helm chart. So to deploy the new version of the application, chart.yaml is to be updated using a nano command. So first, let's do nano in chart.yaml, and the new version is to update it using with the updating the version tag. So just save this file. We can see the index.yaml file that was used for versioning had latest version of 0.3.0, and as now we have updated the version in chart.yaml. Now let's update this index.yaml and push this index.yaml along with the packaged chart to the S3 repo so that that could be utilized in the Jenkins server. Now let's first package this Helm chart with a new version and update index.yaml, and then finally push that to S3 repository. So using command helm package /nginx app, it identifies and checks for the chart.yaml and creates a new package. So the new package named with the name nginx app 0.4.0.tgs with a zipped folder is created and can be seen here. Now let's update the index.yaml to point to the new version, or to get updated with the new version of the helm package. So using command helm repo index dot this update with the new version of the helm chart. This could be verified by viewing the index.yaml. So this is the updated index.yaml having 0.4.0 version. Now let's push this .tgs file, the zip folder of the Helm chart and the updated index.yaml to the S3 repository. So using this command, using the cp command, the updated version could be pushed. So the finally the updated version, that is 0.4.0 version, is pushed or the copied to the S3 repository, and then also index.yaml is to be pushed. So again, using AWS S3 CP index.yaml and the S3 URL, we can push the index.yaml or the updated index.yaml to the S3 bucket. Now let's see how the ECR image was utilized by the Helm chart. For that, we first created the ECR's secret, and that could be seen using kubectl get secrets command. So using kubectl get secrets command, the secret that were utilized were ECR secret. This were the secret that were used for the authentication of ECR with the Helm chart, and the secrets were utilized in the Helm using image pool secret mechanism. So in the deployment.yaml file, we can see a field named as image pool secret, which it fetches the ECR secret repository. So image pool secret, they work like this. Like when the deployment is created, Kubernetes will look at the image pool secret field at the pod specification. It will use the ECR secret to authenticate with the ECR registry. Once authenticated, Kubernetes will pull the specified image and start the container. In our case, the image pool secret was tagged with the values filled, and values had the image pool secret defined. So in the values.yaml file, image pool secret was pointed to ECR secret as a key value. So ECR secret was utilized as an authentication mechanism to authenticate ECR with the Helm chart. Furthermore, to deploy the application using the updated Helm chart, one can simply update the version flag with the suitable version of the Helm chart, and can also roll back to the previous version using just by updating the version tab and deploying the pipeline or building the pipeline again. So further, the evaluation strategy that were employed in the studies were the evaluation of the studies was done by resolving of bugs, vulnerabilities in static code by studying the issues, security hotspot, etc., and were analyzed by Sonar Cloud. Furthermore, evaluation was done by iteratively deploying the Helm chart and looking for kubescore suggestion to improve the Helm configuration and increase the security and vulnerability. So these are the matrices generated by kubescore. So this one is the updated one, and Here we can see the two files, kubescore result.txt and updated kubescore result.txt. In the first iteration, there were a lot of critical cases identified, critical issues were identified, like CPU limit, memory limit, content has no configured security related issue, and image version tag, image with latest tag. So once the each configuration in the Helm chart was updated and the files like hpa.yaml, ingress.yaml, and other configuration related issues were updated in deployment.yaml, service.yaml, and other suitable files. So updated cube score result gave us less critical issues, and most of the critical issues were resolved, like CPU limit were not seen in the updated one, memory limit were not identified, and other image related issues were not identified. uh, Vulnerabilities identified by Sonar Cloud were resolved. Most of them, like most of the critical, like CSRF token, other security issues that were critical enough, that were critically identified, that they were resolved. Now, before conclusion, let's see the application deployed on the Kubernetes and pods running. So, using command kubectl get nodes -o wide, we can see the external IP of the node worker node. So, this is the worker node. And as we can see in the values.yaml, the node port is 3009. So on this node port, the application is running. So now let's go to Google Chrome and see the application by specifying the IP and the port number. So we can see the application is running and is scalable enough to meet the requirement, or to meet the increasing workloads. Furthermore, one can see the pods running using command kubectl pods. So these are the pods running, and the new release or the updated release of Helm can be seen using command Helm list. So these are the different. This is the revision that was. This is the application, or this is the revision that was used for the study. My release. Now also let's see, like let's trigger the Jenkins pipeline and see if the new revision of the Helm application is deployed. So the current latest version of the revision is revision number 22. Now let's trigger the pipeline. Now let's trigger the pipeline by clicking on build now. So the new build has started. One can see the running build by clicking on that build. And now checking the build logs, we can see that the authentication was EKS was made. Furthermore, Sonar Scanner started analyzing the static code, and the image was built, created, and finally pushed to ECR repository. This were the build stage of the image, Docker image, and finally it was pushed to ECR repository. And finally, the application was deployed successfully on Helm with the revision 23 and with the release name by release. Now let's confirm this by checking the Helm list by using Helm list command. So this confirms that the application was successfully deployed with the new revision, that is 0.4.0, that was updated in the configuration of the Jenkins pipeline, and new version that was created using the chart.yaml was deployed in the application. Furthermore, for conclude and conclusion, furthermore for the conclusion, hence looking at the complete demonstration, evaluation matrix, and versioning of Helm chart, we implemented a solution that is efficient enough to analyze the static code, analyze and identify security threats in Helm configuration, securely store Helm chart, and to develop a streamlined Jenkins pipeline that automated the all tasks. We also by using iterative approach, we saw that more than 70% of reduction in critical issues those which were identified by KubeScore in Helmchart. The final version of the application was deployed using the updated version of Helmchart, and most of the critical issues were addressed. Some major issues related to CSRF and some other security issues were resolved from static code to make a secure API communication in application. Now let's discuss the future work. Upcoming contributors can look for exploring multi-cloud deployment or application of Kubernetes services. Analysis can be done to check the deployment time, cost effectiveness, exploring security-related issues. Researchers can also look for integrating an AI-driven solution or can create an ML-based model to identify the vulnerabilities in static code and help configuration. Furthermore, contributors can also look for implementing a real-time monitoring system to detect the spikes and study the traffic workflow in Kubernetes environment. To conclude, more and more iteration can be made to look for issues analyzed by KubeScore and Sonar Club, and troubleshooting can be done to resolve those issues. Thanks a lot.